Okay, now we want to talk about the isobaric process. And iso again meaning same, baric meaning pressure. So here we have a process that is done at constant pressure. And so, if that's the case, the first thing we want to do is calculate the work. And again, the work is negative the integral from V1 to V2 of P dV. But if P is constant, then I can pull that out of the integral. And this just becomes negative P times the difference between V2 and V1, or P delta V, right? So this is going to be negative P delta V. And so we can now use this in the first law in this form. Remember, delta E int is equal to Q plus W. And what I want to do is rearrange the first law now to write it as Q is going to be equal to delta E int minus W, okay? So we have the first law in this form now. All I've done is subtract W from both sides. And now, again, we have a form where Q, the heat being added to my system, is equal not now in the isovolumic process to just delta E int, but it's equal to delta E int minus the work done on the system. And the work done on the system is negative P dV. So this is the same thing as plus P dV. And if we do the same kind of thing we did before, where we let the amount of heat needed to be added to the system be equal to the number of moles times some specific heat times the temperature change, then I get this. Okay? The amount of heat needed to raise the system by some temperature dt, or delta T, is going to be equal to the sum of the internal energy change plus the work done on the system, okay? And here we have the specific heat at constant pressure, since we're under a constant pressure process. And notice, okay, that now we have NCP delta T equals delta E int plus P dV. And this is a little bit bigger, or in some cases a lot bigger, than the NCV dt that we saw from the isovolumic process. So what this is saying is the amount of heat needed to raise the temperature of a gas under constant pressure has a higher specific heat value because I'm not only raising the internal temperature, but I'm keeping the pressure constant while also changing the volume. So this is a process where, let's say, I'm expanding the gas, in which case the pressure would naturally want to change, but to keep the pressure constant, I have to supply even more heat than would be necessary to just raise the temperature if I were holding the volume constant. So Cp is going to end up being larger than Cv, and that's what we will see in just a moment. Okay, so again, we can write delta E int as NCV delta T plus PdV equals NCP delta T, but PdV, using the first law of or not the first law, but the ideal gas law, if I hold the pressure constant but take a differential of both sides, then that's the same thing as PdV equals NR delta T. Well, this would be delta T, or delta V rather. And so P delta V is equal to NR delta T. And so PdV can be replaced by NR delta T. Okay, so now we can divide through by N delta T, and we see that the specific heat at constant pressure is actually the sum of the specific heat at constant volume plus the gas constant. And again, this is because to keep the pressure the same, I have to supply an even greater amount of heat. Some of that heat is going to go into raising the temperature of the gas, as it would be if it were at a constant volume, and then the rest is going to go into increasing the pressure itself. So if I want to raise the temperature of a gas but do it at a constant pressure, then I may have to supply more heat to it to compensate for the fact that the gas could be expanding, and therefore I need to supply more heat to keep it at a constant pressure. Okay, so that is how you can apply the first law of thermodynamics to a isobaric process. And the last process we want to look at is the adiabatic process, and this is one of the most important processes in gasoline engines, thermodynamics of stars. It's found all over the universe. And adiabatic is simply a process that occurs fast enough that there is no energy transfer between your system and its environment. Okay, so this, you can do it either very slowly, so that everything happens, stays in thermodynamic equilibrium, or the process can happen instantaneously, fast enough that there's no chance for energy to escape the system before the system has changed. Okay, so essentially at the end of the day, an adiabatic process is just one in which energy transfer with the environment is zero. There's no heat escaping the system and no heat coming into the system. And if that's the case, then the first law is written as delta E int is equal to W. And what we will find out in the next video, I'll do the derivation in the next video, but there is a specific relationship between the pressure and the volume, and the pressure and the volume are related in an adiabatic process by the product of P times V raised to the gamma-th power equals a constant. And what is gamma? Okay, gamma is the ratio of the specific heats at constant pressure and constant volume. Remember, the constant pressure specific heat is larger than the constant volume specific heat. And if I raise my volume to this power, if I know what Cp and Cv are, for ideal gases, it's very close to 5/3, right? And then I multiply that by my pressure, I'm always going to get a constant for the entire system. So as long as my system is undergoing an adiabatic process, then this relationship will hold, all right? So if I know my initial pressure and my initial volume, I can, and I know what my specific heats are, I can calculate my constant here, and then if I want to know what the volume would be at any other pressure, I can just insert it into this equation, solve for that pressure, and the system will hold. All right, so this is the adiabatic process, and this is the first law written for it. The work done on the process is going to be equal to the internal energy change. All right, hope you enjoy, and in the next video we'll actually see how this equation is derived.